Respected principal, respected principal, Dr. Sister Shiny KP, our today's resource person, an outstanding DRDO scientist, Dr. Raju Venkatanarayana, and all the participants across the country. A very good morning to one and all. I am K. Arunodaya, lecturer in physics, JMJ College for Women. I welcome you all for second day of 5-day national level online FDP on effective pedagogy for science. Let's start our program with a prayer song invoking God's blessings upon us.
I come before you today. There's just one thing that I want to say. Thank you, Lord. Thank you, Lord, for all you've given to me, for all the blessings that I cannot see. Thank you. Thank you, Lord. Thank you, Lord. With a grateful heart, with a song of praise, with an outstretched arm, I will bless your name and thank you, Lord. I just want to thank you, Lord. Thank you, Lord. Well, I just want to thank you, Lord. Thank you, Lord.
Now I invite Mr. P. Satish Kumar, lecturer in physics, to introduce our resource person, Dr. Raju Venkatanarayana.
Good morning, everybody. It's my honor to introduce an outstanding DRDO scientist, our today's resource person, Dr. Raju Venkatanarayana. He is from Chintavaram, Nellore district, Andhra Pradesh. He did his BSc in Sri YNM College, Narsapur, and completed MSc Physics with electronic specialization in 1976. And he was awarded PhD in 1988 from Andhra University, Visakhapatnam. Sir joined in Electronics and Radar Development, LRDE, Defense Research and Development Organization DRDO, Bangalore during 1981 as a scientist B, and worked in the field of radar transmitters, phased array antenna and radar systems, and superannuated during 2016 as an outstanding scientist. Few of the radars designed and developed as a team member and as a project director and got inducted Defense Service. Currently, he is working as a Dr. Raja Ramanna DRDO Distinguished Fellow at LRDE DRDO, Bangalore. Sir published around 12 research papers in various national and international journals, and he received Agni Award for self-reliance for leading the team in the design and development of weapon locating radar, SWATI, during 2008 in addition to various departmental and laboratory level awards. Sir, we are so happy to have you in our midst.
Thank you, Mr.
Thank you, sir. Now, I am glad to invite our resource person, an eminent speaker, Dr. Raju Venkata Narayana, to take over the session. Welcome you, sir.
Presentation, you can put it.
I request all the participants to mute your audio.
Yeah, good morning to all the participants. Thanks for giving me this opportunity to talk to the students as well as academicians, though I am, my profession is slightly different from that. Basically, today's topic is taken as Introduction to Radar for Defense Applications, an effective pedagogical approach. And why start with what is radar and how it differs, the criteria and the situation for the defense applications, and also what are all the various classifications of the radar. If you really see it, different names will be there. We keep seeing the newspapers and the literature, so many types of radars. Why so many types of radars are required? And in the design and development of these radars, what are all the various disciplines involved? Not just electronics, there are many more which we will be going through. And slightly different from the academic nature, what are the various phases which are involved in the radar development, from design and development to induction life cycle till it retires from the service and some other new radar takes over its place. Also, I could collect some information from LRDE regarding what are the indigenously developed radars. Some of the radars also will be presented in due course. The basic idea is to inculcate interest in the basically the students, where radar is not some sort of a Latin or Greek. It can be easily understood, and there is a good scope of participation for the people from all walks of life in the radar development. All disciplines are involved. Everybody has got a role to play in the total development and the induction to designing the new radars, to finding out the needs of the radar for various threats. Because as the threats keep changing, the technology keeps changing. The techniques more or less either remain same or new techniques will be evolved, but the new radars keep developing, getting developed. We'll just dwell on these aspects too as the time goes by. And all of us know the radar is radio detection and ranging. It is an acronym. Is an electromagnetic system for detection and location of reflecting objects. Reflecting objects can be any. It can be an aircraft. It can be a drone. It can be a ship. It can be a boat. It can be a spacecraft. It can be vehicle, and it can be knowing the weather or the environment, or it can be a sea situation, or it can be even a crawling man coming with a weapon who can pose a threat to any of our installations or the storage of equipment and things like that. So basically there is and why we need radars is, can't a human see it? When something is flying, aircraft we see, ship we see, boat we see, but a human has got a limitation. We have got a limited view, limited range of view. The clarity won't be there. If it is a darkness is there in that background, we cannot see the objects. If it's a haze is there, fog is there. If it is raining, our visibility comes lower. If it is a snow, also a similar thing happens. So here comes an equipment which can operate in all types of environment. Not only all types of environment, all types of terrains also. It can be, as you know, in our country we have a wide range of terrains which are there in our borders. One side we have plains, we have deserts, we have forests, we have mountains, we have sea. So in all these conditions also, the threats keep, different threats keep coming in different directions. How to have a surveillance? Once you detect or where the information goes about what information we can give about the threat. In the radar sense, it is called as a target. This target information, how it is generated by the radar and sent to the end user. It can be a weapon, it can be a weapon system. So how this information goes and what activity he does to neutralize these threats. So basically defense radars are for this purpose. Also surveillance, it can also is a part of a fire control. It can be from the aircraft, it can be in a missile system, or it can be by imaging or imaging the threat. It can be over the land. The threat can be seen from a sky, what we call it as a synthetic aperture radar, which will give the clear picture of what is happening on the ground or on the sea surface. Or some radars will have combinations of all these things, not only surveillance, it can track, like that various functions will be there, which will be coming to that. So this is the basic functioning. I put a simplest of the diagrams here, radio detection and ranging. There is a transmitter. What a transmitter does is, it takes some small power microwave or a radio frequency in the designated waveform. That waveforms also will be coming across further, and it transmits through the antenna.
Excuse me, sir. Sir, slides are not running, sir. Okay, sir. Thank you, sir.
Coming?
Okay, sir.
Okay.
Can you just ask whether it is visible now?
It is visible, she says. Is it clear, madam, now?
Yes, sir. Yes, sir.
Okay. So, the radar transmitter we are seeing there takes a small power microwave or a radio frequency and amplifies it to the desired levels, transmits through a circulator which connects the power to the antenna. Antenna is the one which radiates the power into the sky or the sea surface or into the land, whatever may be the radar what we are working on. Depending on that, it radiates. The radiated energy, let us say in this case, goes into the sky. Anything which gives obstruction to that energy, some portion of that radiated signal is transmitted back or scattered back towards us. It's not that total power will be coming back to in our direction, because like a transmitting antenna is having a high directivity in one particular direction only, it will have a higher power. And once that power gets scattered or reflected, some portion, very, very minute portion reaches the receiver. And here in case of some types of radars, what we call it as a CW transmission, there will be a second antenna. Otherwise, the same antenna, what is shown for the transmitter, will receive the power and directs towards the receiver, and whatever further processing and all these activities are done to extract the target information, and which will be displayed. Of course, from the display, it may be communicated to the weapon system, or it can be networked to know at a centralized place the total situation awareness and things like that. And as we know, the target range is nothing but the distance between the radar and the target. The target range is determined by the time delay of the reflected signal. If, let us say, in a pulse shape, one transmission has taken place, for the energy to go into the sky, get reflected by the target and comes back, even if it is taking or traveling with the velocity of light, it takes some finite time. The time between the transmission and the reception will give us the range to tell that with reference to the radar where this target is, how far it is. And also, we know what is a Doppler effect. That is, any moving target is there will be slight shift in the incident frequency and the scattered or reflected frequency. That frequency will give opportunity for us to estimate what could be the speed of the target, whether it is going away from us, where the frequency will be lesser. If the target is coming towards us, frequency will be higher. The difference between the radiated and the received frequency will tell us the frequency shift will tell us the speed of that particular object. And it's not that all the time we will keep measuring only the frequency shift. Sometimes even the stationary target itself can be our target. That also will come to that. Yeah. Next. Yeah. See, this is, I put here only one type of sort of a transmission. When we are with reference to the time, and y-axis gives you the amplitude of the power what we are sending it, or power of the RF what we are sending. So it is transmission is on for some time. That time what we call it as a pulse width, and that will be repeating after fairly longer time. So between these two transmission pulses, all our target information lies. If due to some reason, let us say if the target is a little far off, then there is a chance of receiving energy after the second pulse. We will not know whether it is due to which pulse the energy is coming back and things like that. That what we call it as a ambiguous range. Here we have talking of the a radar which is having, there is no ambiguity in the range. All our intended targets are getting reflected and reaching back the receiver within before the next pulse is transmitted. And another
Sorry to interrupt you, sir. PPT not running, sir. Okay, sir.
No, sir, continue.
I can continue. Then next, another important aspect in the typical radars is what we call it as a line of sight. What is the line of sight is, suppose it is clearly brought out here. Can you give me the cursor? If this is the radar antenna which is radiating, at this portion, let us say it grazes the whatever is the terrain. So if some aircraft is there here, this radar will not be able to see. The Earth's curvature itself is shown affecting the or shadowing our vision towards the target. If based on this distance, let us say here none of the things below this line can be seen, above the line can be seen. In the same way, if you raise the height of the antenna, let us say, further distance it can be seen. So this is what we call it as a line of sight. That is because as the electromagnetic waves travel in straight lines, unless there are special weather conditions in which there is something called as a duct propagation that right now we are not touching on, or we can touch upon that aspect now also. Particularly under sea conditions, some amount of diffraction takes place, and the radar will be able to see the targets which are beyond the horizon. That what we call it as a over the horizon radar, which in general are used for very long range, maybe in 1,000 kilometers, 2,000 kilometers of that order, sitting at one place. Maybe near the coast, we can have a look at what is the ship which is 1,000 kilometers from us, what is its movement and what are its characteristics, what is its speed and things like that. And the technology is matured enough now to even develop a radar. In fact, they say the OTH can be used even to look at some Coca-Cola can which is lying on the sea surface. That kind of information can be obtained. But in general, whatever radars we are going to talk now, we are taking that line of sight limitation. Yeah, next. Then coming to, as we just saw, so radar transmits electromagnetic signal. Portion of the transmitted energy is intercepted by the target. That interception also, it's not that all the types of surfaces, even if suppose you take an aircraft, it's not going to reflect the same proportion of energy towards us from all directions, depending on where suppose aircraft is approaching us. Some amount of energy will be reflected back. If it is going across, different kind of energy will be reflected back. What we call it as, based on the aspect angle, the amount of energy reflected back to us will keep changing. And once this signal reaches the receiver, we'll collect it and beat it down to lower frequencies to extract the information about the target. So the extraction of information is a wide-ranging topic which is involving receivers, which is involving the signal processor, and if the signal is weak, The signal processor also will have different type of configurations, like integrate a number of echoes to extract information, things like that. Then there is something called as a data processor which follows, which narrows down and gives the information. Radar information, basically what most of the radars expect is, one is what is the range, what is the azimuth, or with reference to north, at what angle this target is with reference to the radar, with reference to the north, and what is its elevation. Elevation is nothing but it gives the at what height he is flying. So r, theta, phi. So if r and theta alone are given, it is a 2D radar. If r, theta and phi, range, elevation, azimuth and elevation information is given, it is a 3D radar. Or if range, azimuth, elevation and Doppler also is given, that is called as a 4D radar. Yeah. Here comes to radar subsystems, and some of the words or the terminology what comes very frequently across. The transmitter. Transmitter is what, let us say, we are not going to a oscillator type of transmitter. We are going for an amplifier type of a transmitter, let us say. There are certain things called as microwave tubes. These microwave tubes, from a low signal, it amplifies and gives a very high power. Let us say it can be even a kilowatt level or even a megawatt level power, which gets connected to the antenna. This is nothing but a power amplifier in the transmitter. And as the technology progressed, there are solid-state transmitters too. A single solid-state device cannot give that much power levels, so a number of devices are used and the power is combined. Power is combined to get the higher power. So these are some of the terms only I am explaining here. In the same way, antenna, there are different types of antennas. There are reflector antennas, which you would have seen here and there, including in the airport, which keeps rotating. And that we call it as a reflector type of an antenna, which a radiating element which can be a dipole. And also, most of these current day arrays are what we call it as a phased array. Phased array. That means instead of a single element, a number of elements will be radiating. It can go from, let us say, 40, 50 radiating elements to, it can be even thousands. There are certain things which is having even 20,000 elements which radiate. More number of elements are there. It will enable you to put these transmitter beams in a desired direction more accurately. The passive devices are there only when one transmitter is there. But at the receiving time, there are a number of channels and things like that. That is what we call it as a passive array. In the active aperture, what happens is, throughout the plane of the array, a number of transmitters and receivers put together will be there, integrated into the antenna. That means instead of one transmitter and one receiver, the radar will have, let us say, 5,000 transmitters, 5,000 receivers, and the combined effect, whatever the process way, which way we are doing it, it can be seen signal processing and down the line. And also, there are conformal arrays, what we call. That is, if aircraft is there, it is having a nose cone, or it is having, it's not a planar surface at any place. If you look at an aircraft, so the antennas there, instead of a planar, it will conform to the shape of the body of the aircraft. And it can be in an aircraft, it can be in two sides, or it can be a nose cone, depending on the application of this particular radar. And on all these things, antenna always goes with one item called as a radome. That is what radome does is, it is an RF transparent material. At the same time, protects the sensitive elements of this antenna from the vagaries of the environment, the humidity, these kind of things. This is also a very, very important element in the radar. A lot of chemistry also is involved in the development of these radomes. And once the radome is made, it is the radome which is facing the outside environment. If you really look at it, the radar, once it is deployed in the field, let us say, it has to work in the field maybe for 20 years, 25 years. So the life of everything, whatever we are talking here, is substantially higher and higher. Otherwise, radar is there, but even if a small thing fails, the entire thing comes to a standstill. It doesn't serve the purpose. So we will come back to that, because most of these radars are 24/7, and it will work for all the 365 days, but for some maintenance time in between and things like that. If somebody has to work like that, how much reliability has to be brought into these systems, each and everything, whatever is mentioned here. In the same way, in the super receiver, when we go, we call it as a super heterodyne receiver. That is, the RF signal, when it goes, what comes back also is RF. That will be in a megahertz range. That has to be brought down to lesser frequency, maybe let us say 30 megahertz, 60 megahertz of that order, in 2 stages or 1 stage. If it is a 2-stage, it is or more, it is called as a super heterodyne receiver. Having brought down to the lower frequencies, then the information extraction from the received signal will be much better. And then is the noise. This is one very, very important thing. Once we understand the noise, we understood the radar. That's what a famous saying. So this noise from so many places, it enters the system. So how to reduce this noise, or in spite of this noise, how to extract the signal which is coming from, or information which is coming from the target can be extracted. And bandwidth is one important thing. That means whatever signal we are sending it, what is its bandwidth? Higher the bandwidth, higher the resolution we get, or more clarity we get about the target information. And pulse compression, of course. When we go back to the single pulse, can you go back to that pulse? What we put previous slide. Yeah. Here, this along the width of the pulse also is nothing but some range only. So in that range, if a target is there, whether it is at the start of the pulse, the return is there, or at the end of the pulse, if the return is there, we will not be able to make out. So there is a technique called as a pulse compression. The total pulse width is split into a number of sub-pulses. When sub-pulses are integrated, the resolution what can be obtained will further improve. Go back to that. I'm slightly going on a sort of super view only, not getting into the total details or depth of any of these things, because the coverage of the total radar in an hour's time is slightly, I found it slightly a difficult thing. That's how this kind of a presentation is made. The signal processor, we know the terminology, what are the technique what is used is moving target indicator. That is to extract the information about only the moving targets, because even if there is a reflector which is not moving, energy comes back to the radar. So whatever energy comes back to the radar, it will be from wherever the reflector there, whether it is stationary or whether it is moving. So how to extract the information? That moving target indicator is the technique. And if you want very, very weak signal is coming, as per the target is smaller, let us say, then a number of pulses will be coherently integrated. Coherently integrated means their phase also must be known. And Doppler filtering also is done, so that each filters, suppose there are some 12 filters, between the two pulses, whatever is happening, these 12 pulses further will bring the clarity on which Doppler across the total Doppler. Then radar computer. Nowadays, in fact, though it controls the radar, scheduling, the data processing and things like that, it does. As the time progressed, the radars are becoming more computer-centric. There is a lot of computer science. Now, in fact, even the AI also is slowly getting into that is artificial intelligence also, using the radar background information and building and mapping and a sort of a force measure as a sort of a force multiplier sort of a thing. Same radar, how to get the more juice out of it, more information out of it. The AI also started playing in a big way. Artificial intelligence and the machine learning also is an important aspect here now. Radar display. This we see it normally, even in the TVs we see sometimes. There is a plan position indicator. Sorry, there is some mistake there. Plan position indicator (PPI). And also sometimes the display will be range versus height indicator, or a B-scope where the range versus the azimuth type of information, or so many, even a 3D picture can be seen. Like that, the displays have also gone, they can be developed the way you want, or you extract more sort of information from that. Display is more important in the sense that anywhere the machine is one, and the more important is the man behind it. So without causing much of a strain for if somebody has to operate the system for 24/7, even if he works for only, let us say, 2 hours, 3 hours for the radar, not generally radar operator will not be able to work more than 3-4 hours, because it's a strenuous job and he loses the sort of a concentration. So what normally done is we have to see that it has to be as human friend or operator friendly as possible. At the same time, without loading the operator with additional work, the display has to give him as much information as possible. The other electrical engineering portion of it is the diesel generators are there, because most often there will not be power mains or electricity board power available for any of these radars. So generators, the radar has to be self-reliant on the power source also. So mostly the diesel generators are integrated along with the radar equipment, and AC, whatever is generated or whatever is fed to the radar, n number types of DC power supplies, DC-DC converters, AC-DC converters, is a good sort of a work goes there. And also all these things have to meet these standards with reference to what we call it as a electromagnetic interference and the electromagnetic compatibility standards. Why they are required is, one radar which is operating, there may be a communication equipment nearby, or there may be some other radar nearby. No equipment should interfere with the operation of the other equipment. So everything should be compatible to each other. This is what all these things also matter here. And command and control. is one important aspect. It can be a digital communication, all types of communication. It can be radio communication, it can be satellite communication, like that. All communication also mostly goes with the radar control and networking. In fact, sitting in Delhi, somebody can see what is the air scenario at Bangalore. This is the type of a way the radars are networked. So that when we deploy the radars in borders, it's not that even a general goes and sits in the border. It doesn't work out that way. So, but sitting in Delhi, he can make out what is the air scenario, or what is the, as the radar application maybe, what is the scenario there. That kind of a facility also radars provide. This we went through. So what we call it as a range. This range difference changes from almost on different radars, from a few centimeters to thousands of kilometers. So all radars cannot do all the jobs. This is one basic thing is there. Based on the application, the radar will be developed. Based on the threat, its characteristics will be built. The azimuth we know, always with reference to the horizontal plane, with reference to the north. Elevation is a height information, in fact, really speaking. Doppler, clutter. Clutter we call mostly it is reflections from the unwanted echoes. The MTA we saw line of sight, we thought go to the next one. Yeah, some of the other terminology what we use in the radar, probability of detection. In fact, here the mathematics is very, very important in the design of the radars. And nobody can say that 100% probability I will give this particular target. The reason is, if you design a radar, if you want a 100% probability of detection, it is as good as it becomes a huge system. So the probability theory is used widely. Some radars, they say that 50% probability of detection. Some they say 0.9 is the probability of detection. So mostly the military radars, probability of detection will be of the order of 0.9. And if you are using the radar for any, let us say, killing purpose, in the sense that it can to kill the aircraft or to neutralize the missile and things like that, all those n number of elements, whatever are occurring in the system, all these probabilities will be multiplied. We say that kill probability is this much. There is no 100% killing probability, or there is no 100% probability of detection. And the probability of false alarm, in spite of all our processing and things like that, in addition to the target, one odd unwanted thing also gets in. If in fact, this will be the order of 10 to the power of minus 6 of that order. To say that if 10 to the power of minus 10 to the power of 6 inputs come, there is every probability that one is, it's not there. It is just it is shown as a target. Range resolution. Range resolution is, if there are, let us say, if I say that this range is 375 kilometers, this 375 plus minus what? So that we call it as a range resolution, which also helps if two, let us say, two aircrafts are flying together, whether they can be designed as two separate targets or not. In the same way, range accuracy, what I told is range accuracy, where if you can distinguish between two nearby targets with what resolution, that is, that term of range resolution is used. In the same way, azimuth resolution and azimuth accuracy. It is at, let us say, at 90 degrees with reference to the radar. This 90 degrees is 90 degrees or 90 minus 0.1 or plus 0.1, that the accuracy will tell. At the same time, if there are two targets flying, let us say, in the same sector, separated by a distance with whatever is the azimuth subtended at the angle subtended at the radar with water resolution, they will be seen as two separate targets. In the same way, elevation resolution, all these things are used particularly when the aircrafts are flying or number of boats are there on the sea surface. We do not know whether if you see really the coastal line, sometimes there will be thousands of boats when what we see in the coastal line, whether we all 3-4 boats together will be seen as one, or we can clearly distinctly see each and every boat whatever is available there. This 2D, 3D, 4D radars, we spoke about it. Yeah. Yeah, this in the functions of the radar, what radar first does is, radar is given a coverage. Let us say some radars, they say you have to cover the 360 degrees. So the antenna keeps rotating with a particular rotation rate, what we call it as a rotations per minute, let us say 10 RPM or 15 RPM or whatever may be the thing. So if you want faster update rates, the RPM has to be higher. Based on that, so search is done in a particular fashion. When the search is done, if there is a target of interest or if there is some obstruction, it will be detected. Once it is detected, based on a number of criteria, whatever are set in the system, it is classified as a target. If that target is any way sort of a threat to you, sometimes till we understand that, we do it whether what we call it as a track while scan. We keep searching at the same time. By the information what we are getting for each and every scan, we will classify it. Also sometimes use the identification friend or foe type of what we call it as a secondary radar to know whether it is our aircraft or whether it is enemy's aircraft. That identification friend or foe type of equipment will be put in the integrated in the what we call it as a secondary radar integrated with the radar system. Or if you need the threat information, suppose if the target is very fast, sometimes we need to have a specific look all the time on that without losing even sight of it, even for a very, very small time. That we call it as a track. So the update rate of the radar information about that target will be made much faster, and it keeps getting tracked, and which will give the radar a highly accurate information. Then sometimes radar is used even for imaging, what we call it as a synthetic imaging radar. The basic functions are this. Go back. Oh, equation is missing. No, go back. Right? How is that equation? I have seen it.
This equation is coming.
Yeah.
R.
No, or what happened? Equation, it has come here. Can you take a minute's break, madam? Hello? They are not there, huh?
Not there.
Okay, sir.
Yeah. Something is, some equation is missing here. Why this? What is this?
They are not there.
No, in the printout it has come. Can you put it, or there's no way to put it, no? Huh?
No.
Oh, I'm sorry about it. Anywhere else it is there? Or? No other presentation is there.
No other software is there.
Huh?
No other software is there. And only it is there.
Okay.
You see online.
That's why okay. Okay, go back. I'm sorry about it. I will orally will tell. Yeah. This is a radar range equation, which is in fact very critical for the understanding. Unfortunately, it is missing here. So this is radar range r to the power of 4 maximum is equal to, I will put it this way, it is directly proportional to the power transmitted, that is PT, and also it is gain of the antenna is GT. So this r to the power of 4, it's not R, is proportional to GT square. That is, because we have a transmitting antenna, same antenna used while coming back in the reflection also. So the transmitted power is directly proportional to, whereas here the gain square, r to the power of 4 is directly proportional to the GT square, and more range is there if you cross section is more. That is very sort of a common type of an understanding. If the object is bigger, more reflections will come. That's what we call it as a radar cross section, though it is also a function of the aspect from which we are looking at the target. And if the wavelength is lesser, range will be better. If minimum detectable signal, whatever your receiver you are putting it, if you are able to reduce the power of the minimum detectable signal, you will get a more range from the radar. This is how the radar range works. I'm sorry about it. Hope I have conveyed. At the same time, the gain of antenna is depending on the aperture of the antenna. Suppose if the bigger antenna is there, the gain will be bigger. If the gain is bigger, you will get more range. At the same time, every place you cannot put bigger and bigger antennas. Reason being, based on the application, your resources by way of your weight, volume, size, and things like that are given. Based on that, with a trade-off, all these aspects are adjusted. Yeah. Then, when we have n number of frequencies, let us say, you can go to this next one and then come back to this. See, radars in general start working from HF to millimeter waves. So the frequency band minimum most radars used is around 3 megahertz. 3 megahertz to 30 megahertz here. What we are talking the horizon surveillance radar work around in that particular band. Some VHF radars also are used for very, very long range surveillance. Like that, over the years, whatever are developed, almost it is sort of a thumb rule that if it is a tracking radar, you work in these frequencies, you don't need to study all the rest of these things. So just sort of a gist is presented here. But the idea here is to say that depending on the application of the radar, the frequency is chosen. No, previously. The choice of the frequency is selected based on it is so one half is missing here. Trade-off analysis. The aspects are taken into account is what is the feasibility and what is the technology readiness level. This is one important aspect. One is the techniques available with us. Other one is technology available. If you put otherwise in mathematical equations and things like that, sometimes you may land up with a power where there are no devices to give that kind of a power. So technology readiness level, whether it is with us or which can be obtained, that also is one aspect to work when we are deciding the frequency. Of course, performance take the front seat. The weight and volume. Say, for example, if a radar has to be developed for a detection of a crawling man in as a perimeter defense. The weight and volume also matters because the operator also can carry up to certain weight only. Truck also will have some limit. It can be a 4-tonner, it can be some 10-tonner or a 30-tonner. It cannot be infinite. So like that, these cost also is one important aspect. So a trade-off analysis is done on all these aspects before we finalize and say that this is the frequency I work to get this so-and-so performance with this so-and-so weight and volume, and its cost is going to be this much. Next. Yeah, is this over? Yeah. And also, when we keep seeing, in fact, a very funny question somebody has asked also, if a radar is doing tracking, surveillance, detection and things like that, can't this one radar can do all these jobs? Why we have to keep developing the radars? Why it is like a sort of green field type of a thing, which eternally keeps running? The reason is all radars cannot meet all the requirements. It is a application specific, performance specific, and not only that, the obsolescence and things like that also keep playing a major role here. You see, for example, targets. Our targets can be in aircraft or a drone or a ship or a boat or a men or a vehicle movement in the field or a missile, or it is its purpose is only for imaging of a stationary target or a moving target. And a medium and environment, some radars work for sea surface, some for land surface, some may work even under the land also to identify the objects like IEDs and things like that. Foliage. Suppose somebody is walking in a forest, the helicopter has to locate him. That will have a different technique and a different frequency, and that's how they are classified. And through all radar, for example, if a terrorist or somebody is behind a wall, we don't have access to physically see him. There is a radar available which can see through the wall. What can see through the wall cannot work for the other type of applications. See-through wall radar, where it is a very, what we call it as a ultra-wideband radars are used, and they have to be a very, very small so that they can be carried anywhere and it can be seen. But radars are developed to see through the wall. Even sometimes we can even get the signature of the heartbeat of the whoever is there across the wall. And platform, some are vehicle mounted, some are ship borne, some are airborne radars, or some are put in UAVs itself. And of course, all of us know even satellites carry the radars. Range-wise, we can classify very short range. If across the wall, if I have to see, I don't need 100 kilometers radar because he is a threat to me within meters. So short range radars. Or a crawling man is there in a perimeter, maybe a 500 meters, 1 kilometer, that kind of a thing. Some aircraft, let us say, 50 kilometers, 100 kilometers, 400 kilometers maximum. And long range, there can be some radars which have to see the, let us say, the incoming intercontinental ballistic missile based on its height and clearance of the line of sight. We can see him even from 1,000 kilometers or 4,000 kilometers of that order. So based on that also radars are classified. Some people call it as a short range radar or a medium range radar or a long range radar. Based on the operating band frequency, I call it a L band radar or a S band radar or a C band radar. The antenna technology, so more and more technology development, particularly in the solid state devices, has led us into this new technology of active aperture and things like that. So we call it as a electronically scanned array or a active aperture radar. Like that, there will be n number of radars. If you go through the world literature, every day practically you can say that one new radar developed across somewhere in the world has seen the light of the day and it is inducted. That is the kind of a volume for the total sort of even a business opportunity for these industry houses. Definitely the requirement is there for huge numbers at any place, and it is the limitation or a constraints of the finances. Somebody may have 10 radars, somebody may have 20 radars, that kind of a thing. Otherwise, with our long borders, where we have a huge sea line, so much of a land borders, these radar requirements is ever emerging, and it is a sort of a continuous process, not only for obsolescence management, even from the threat point of view also. And depending on the waveforms, some are continuous wave radars, some are frequency modulated continuous radar, pulse Doppler radar, or low probability intercept. That means the radar will radiate such low powers that the enemy cannot capture our signature and tell that there is a radar available there, let us neutralize it. So that their radars are called as a low probability intercept. So, and based on the threats or targets, what we just now spoke, ground-based radars, normally tanks, jeeps, moving or crawling men hidden behind walls, gun firing, missile launchers, and under the surface, such as IEDs, they are normally in the mines and land mines and things like that, no? That kind of a very, very portable radars, yet giving the safety to the operator so that he himself doesn't get affected. Sea surface, such as ships, boats, and periscopes. In the ships also, some periscope comes out and have a total picture, and then again it gets into the ship. That kind of a thing also have to be detected. Airborne, such as aircrafts, helicopters, UAVs. So we call it as a UAV radar, or it is a radar for ballistic missiles and things like that. And spaceborne, such as satellite launch vehicles. And another problem, you would have heard it, the space debris. This is a nuisance for everybody. Like we don't have a traffic control, what kind of a problems it can create. Even for space also, the satellites and the traffic of these debris creates a problems for the satellites. So, or the whatever is the vehicle is put in the sky. So that also has to be monitored. Yeah, and we'll come to the point because we have so many sort of a subsystems, so much of a technology. Really speaking, what I have mentioned here only a few. Otherwise, the disciplines what are required for radar design and development is wide ranged, very, very wide ranged, and to develop the domain specific knowledge in each and every these disciplines which are required by the radar, that itself is the total research activity. The electronics and semiconductors keep changing almost sort of a thing, very, very, very fast, and that is the one which will keep us sort of a you run to stay where you are type of a situation, particularly in semiconductors, because the development and the technology is growing so fast. The electrical, electromechanical, power, DC and AC, The mechanical engineering is very, very crucial aspects for the radar. Thermal and structural engineering, because there is a shock, there is a vibration, there is a structural integrity is required for the equipment, whatever we put there. Without mathematics, physics, chemistry, I don't think any of the remaining things will ever survive also. So that is very important. These are all the important fields. The computer science and is getting into more and more into the radars. One is from the radar controller, the processing, the data processor, and all these points of view. And not only that, now even the machine learning and the artificial intelligence also are coming in. The environmental engineering that we should know, atmospheric science, because once the RF is leaving the antenna, it goes to the target and comes back. Entire your propagation is in some atmosphere. So that atmosphere has to be thoroughly understood. Not only troposphere, stratosphere, or this one, including our land. What is the type of a land or soil structure or soil science? These are all depending on the application, depending on the radar, what we are addressing. Some of those aspects are to be thoroughly understood and put into the design. As some mitigation at each and every place will be required. And communication engineering, fiber optics, whether it is radio communication or whether it is a line communication, these are all areas which are required. And the reliability and safety engineering, particularly the reliability of the equipment and the safety of the operating personnel is very, very important. How to bring up the reliability. Once it is expected in some radars, even if it is continuously switched on, it should not, it should perform giving out the performance what is expected from it. For let us say some 5 days, 6 days, things of that nature, continuously it is switched on and it should keep working. That kind of reliabilities are what are expected. Even when it is transported from one place to the other, you go and switch on that other place, it should work at first attempt itself, because that's how the military requirements also, the defense requirements are such. The reliability, what is expected from this equipment and how to bring in that reliability into your design. This is one very, very important aspect. This is we say that God delayed this, God delayed, and things like that. If you really see it, what is all, see, some user will tell that I need this radar. Okay, yeah, need is identified. And how to specify that radar, how you can tell that these are the quality requirements, qualitative requirements of this radar. This range required is so much, this performance is this much, its reliability is this much, its weight volume is this much. All those things will be worked out. Then a sort of a conceptual design will be done. Once conceptual design is done, a sort of a preliminary design is done. And then once that particular phase is over, once we start designing and going into the more and more detailed design and is done, and the development starts. Once developed subsystems are available, they're all integrated. Then that after all are integrated, you do your own test and you evaluate with the threats for which we are working, we may not have, but somehow you have to prove that even if that threat is there, it will work, that kind of a thing. Some are tested with the simulation, some are tested with the actual test itself. It can be a gun firing, it can be with a missile, or it can be a ship, or it can be a satellite, or it can be anything. These are all the test targets are required. Once we prove in, let us say, in R&D organization, and evaluate it, and it is working to the satisfaction of the main customer. Our customers are who? The Army, Navy, and Air Force. and some of them are paramilitary forces like BSF and coastal surveillance and that kind of agencies who are there, who requires these systems. So these are then these R&D agencies here, at least in our country, it will transfer the technology to the production agency. The production agency is the one who are going to produce the numbers of the proven technology, and then hand it over and or sell it to the services. So production is done and the user deploys it and operates it. We have to get the feedback of the deployed systems, and based on the feedback, some modifications or corrections or mid-course corrections, till it is there in the field, you are responsible for the operation for it, and any changes or any new requirement coming up and things like that, and also obsolescence management. This is one important aspect what everybody has to go through. Even if I am using a chip, when a radar life is expected to be 20-25 years, it should have the roadmap of that chip manufacturer also, whether he will support us for the next 30 years. That kind of a thing also is done. We go through the roadmap of his business for at least 2 decades to see that, okay, I can use this company's chip. He is also a sound company. He is going to supply us even if at a later stage. That kind of a workout is done. And of course, after working for 20 years, the system retires. System retires in the sense that it is no longer economically viable or effective in the field. So then go back to the first step, that is the need identification, and again start the total process. And I can only tell one thing, in our country, what it used to be a development need to induction cycle of maybe 1.5 decades and things like that is very much is reduced by various means. Now, even the user expects you to deliver the radar once he specifies in 2 years, 3 years of that kind of an order. So it is all, that's how the things have changed the shape. I will just briefly mention before this one, non-military applications also. So many radars are there, but there are agencies who take up, and based on a particular requirement and this one, if there is a overlapping interest for the defense, we at defense radar agencies will take up the job of that also for the development. For example, remote sensing, coastal surveillance, air traffic control, law enforcement and highway, aircraft safety and navigation. When aircraft is flying, whether cloud is there or whether somewhere thunderstorm is there and things like that, somebody has to tell him so that it will aid his navigation. And ship collision avoidance and space vehicle docking. Yeah. Now I will quickly go through some of these indigenously. I have time, madam? Hello?
Sir,
20 minutes.
sir, 10 minutes, sir.
Huh?
10 minutes, sir.
Okay. I will quickly go through indigenously developed radars. Very few of them I have taken. Battlefield surveillance radar is one system. This is basically for the moving vehicle in the borders. It can be a crawling man, it can be a walking man, it can be a group of men or moving vehicles. This is the radar which is developed and inducted in huge numbers, maybe around thousands, because we have a longer borders. Next. This is one radar. What you are seeing at the top is this is the antenna. This is with some RPM, I think 12 RPM it moves, it gives a 360 degrees coverage. This is the targets, aircrafts, helicopters, and UAVs are the targets for this particular program. And these are already inducted into the Indian Army. This is a 3D along with the Akash weapon system. Same thing is given to Air Force, Army, and Navy too. Yeah, next. Yeah, this is the 3D tactical control radar. When we developed one system, mostly we'll also see when we are going for the next program, whether we can reuse the technology. And it's not that every time, we have to start afresh and things like that. Some background is developed, some information is available, some technology readiness level is much higher. Let us say almost, if we create the technology readiness level, let us say from 1 to 10, we'll also see whether we are beyond above 6 or 7 or something like that. So that with a little bit of effort, we can make it into 9, and that kind of this product is given to the users. This is it is mounted on the ship also. Yeah. Next. This is one thing you would have read, and most of our, including students, would have gone through what is a Akash weapon system. Akash is a surface-to-air missile system. When there are two radars which are involved in this Akash weapon system. One is the 3D central acquisition radar, which was just now projected. That radar gives information to this fire control radar. This is a multi-mission radar. So it tracks and gives accurate data to the launcher so that the missile takes off from the launcher. Once the missile takes off, there is some command guidance also from the radar for the missile on its dynamics. This is the radar which is specifically developed for flight level radar for Akash weapon system. This is one radar. I can only tell very briefly. In the 80s, when for the similar requirements the radar is developed, it used to be on 2 10-tonner vehicles. The technology in the semiconductors and subsequent the compactness in the system, integrated systems availability and things like that. Now this is almost around a 90 kg radar. So which can be carried by the even mules to reach those heights and deployed, and it gives the surveillance up to 50 kilometers for a 2 square meter target. These are also deployed. Yeah. The same way, this is developed for Air Force with a 50 kilometers range. And you can see here it works up to even minus 30 degrees centigrade is ambient. And in one of the mountain regions, they deployed a radar. Photo is shown here. That is called as Ashlesha. This weapon locating radar, you would have heard of the what we call it as the guns. It can be Bofors, or it can be so many 105 or Howitzer and things like that. When the enemy gun fires at us, this radar, what it does is it tracks the shell and backward extrapolates and gives the location of those gun launchers, rocket launchers, motors, and also to neutralize that gun, enemy gun, our gun fires towards that. So whatever shell or a rocket which is going from our weaponry, that also is tracked and tell the operator whether he needs any correction or whether he could successfully neutralize the enemy gun. This is one radar which also got developed by us, and huge numbers are deployed. In fact, this is in the recent past. Around so many radars have gone into the field. The shelling across the border has come down. It is a very, very effective radar. And I can also, with humility, I will add that I happen to be the project director for this radar development. Yeah, this what we are talking is low intensity conflict radars. That is a ground penetrating radar to detect the mines and things like that. Of course, one vehicle version, one handheld version are developed, and also through wall imaging radar, one tripod version as well as handheld version also are developed. And this is basically for, the first one is for mines and IEDs and things like that. The second one is for people detecting the human beings behind the wall. Yeah, that's all, no? This is the last one.
Yes, thank you.
So with this, I conclude my presentation with a sort of a thing. The aim was to bring some amount of information and interest in the students also, that this is one area not only for the sort of a job or from that point of view, so many disciplines are involved. The research is vast and it is a continuous research which is happening. And as far as the need is concerned, it is ever increasing a need, whether it is in the design or whether it is in the production or whether it is the anything for that sort of a thing. A good scope as well as a good need and a sort of a effective tool even to serve the country. But almost directly, serving the country. These kind of a, are the important aspects of this life, and my request to the academia also. Yeah, any
Are there any queries, sirs and madams? I request you, if you have any queries, please type them in chat box. Sir, we have no queries, sir. Thank you for wonderful session, sir.
And
Thank
I
you,
am
sir.
not sure whether this is the type of a thing what you were expecting or.
Really, it is very informative session, sir.
This is because I am talking to the academicians. I am not talking to the sort of equations or your theory and what normally you keep handling and day to day. This is actually a sort of an applied science which is goes into a product, that kind of a.
Okay, sir. We have some idea on transmitters, receivers, sir. So it is easy to understand, sir. Thank you, sir.
Thank you.
Thank you, sir, for your presentation on Introduction to Radars for Defense Applications, an effective pedagogical approach. Sir, you enlighten us with the knowledge of radar, radar subsystems, commonly used terminology in radars, functions of radars, radar equation, radar frequency, classification of radars, system engineering life cycle of the radar, non-military applications of radar. Thank you, sir, for showing us different types of radars. Thank you for your information session.
Thank you.
Now this is the time for vote of thanks. Now I would like to propose vote of thanks. First, I extend my sincere thanks to our resource person, Dr. Raju Venkatanarayana, for accepting our invitation and sparing his valuable time for us. Thank you, sir, for your interesting and highly informative session. I thank our management, Dr. Sister Teresa Magade, correspondent of our college, Dr. Sister Shaini KP, principal, and Sister Sharda, vice principal, for their continued support and guidance to organize this FDP. I also thank Mr. Murali and Mr. Ravi for their technical support. I wholeheartedly thank all the participants for making this second day FDP program successful. Thank you, one and all.
I should thank Mr. Ayush also, who has helped me in the total activity.
Thank you, sir. Thank you, sir, for your support. Okay, sir, today's session is closed.